needs to be removed from the solder connection with an appropriate solvent. The last consideration for hand soldering using lead-free alloys is when performing rework. Let's take a look at a typical component removal using a vacuum extractor. A general starting point is 355 degrees C, which is 40 degrees C higher than for tin lead solder. This should be sufficient for most vacuum extraction operations involving lead-free solders. We'll need to apply a small amount of flux onto the joints to be desoldered. There are a variety of different ways to apply flux. Remember that the purpose of this flux application is to speed up the heat transfer between the desoldering tip and the solder joint. Always make sure to follow your company's recommended procedures for flux application and cleaning. Now let's watch the removal operation using the vacuum extractor. The process is similar to through-hole rework using tin lead solder. For more information on through-hole rework, see IPC DVD 41. In this final section, we'll be examining the attributes of a typical lead-free connection for a through-hole component. We'll be comparing the lead-free joints with their tin lead counterparts, so you'll be aware of what to expect when evaluating the lead-free connections. We'll also be looking at some of the variations that may or may not be acceptable. This is a good example of a preferred or target through-hole tin, silver, copper solder joint. Notice how the solder feathers onto the land and up onto the lead. The solder fillet is curved inward or concave. The solder covers all of the land and the lead. The texture is a little bit grainy. The outline of the lead is visible beneath the solder. The amount of solder here is just about perfect. Here's one now with a little bit less solder. You can see that there is still some graininess, and the coverage is even. The fillet is concave. This solder joint is perfectly acceptable, even though there is less solder in the connection. Now here's another one with quite a bit more solder. The important thing to notice is the angle of contact between the solder and the metal. Proper wetting is indicated by a solder contact angle of less than 90 degrees, which is a square or right angle. The lower the contact angle, the better the wetting. As you can see, there is a range of acceptable solder joints. You will be expected to know an acceptable solder joint from a defective one before you begin soldering with lead-free alloys. Now let's look at some solder joints that are considerably less than ideal. This is a cold solder joint. Notice that the surface of the solder is even duller and grainier than a typical lead-free joint. This is caused by insufficient heat. This is a disturbed joint. You can see that the solder shows stress lines similar to the foothills in a mountain range. Movement during the cooling process can cause this condition. This is a fractured joint. The component lead may have been moved after the solder solidified. Clipping the lead too close to the solder can sometimes fracture the joint. Here we have a burned board. This was caused by contact with a hot soldering iron. And these are some additional examples of thermal damage. This is a lifted land. Lifting can be caused by pushing or pressing down with the hot iron. Failure to allow cooling between heat applications can also result in a lifted land. Lifting can also indicate that the iron was left on the board for too long, or that too high of a temperature was used. This joint has excessive solder. The fillet is not concave, and there is solder flowing over the edge of the land. Too much solder was added to this joint, and we can't be sure that proper wetting has occurred. This condition is called solder bridging. A bridge is an electrical path that was not intended. Here is a solder projection, also known as an icicle or a peak. These are typically caused by excessive solder or insufficient flux, and by the iron being too cool or not being removed quickly enough. These are solder balls. they can create electrical shorts by lodging in between two circuits. Here's an example of non-wetting. The solder does not feather to a thin edge, and some of the base metal is partially exposed. Another type of imperfection is the blowhole. These are usually caused by gas escaping through the solder as it solidifies. If there is any moisture or solvent inside the hole, or excess flux, this can create a blowhole as the gas expands and escapes. Although some of these conditions are always unacceptable, many of these imperfections could be allowed in various degrees, depending on what type of product they would be used in. For example, we'd all expect that any aircraft or medical electronics would be highly reliable, but we may be able to live with some minor cosmetic imperfections in a portable CD player as long as the product works. The IPC A610 has 3 classes of requirements based on the final use of the end product. Class 1 is for consumer products. Class 2 is for business and computer products. And Class 3 is for high reliability electronics, where failure is not an option. The specification and the class of requirements that your company uses to inspect solder joints will be clearly explained to you. Some companies build a wide range of products with different requirements. Other companies build only one class of product. Part of your job is to make sure to always apply the right criteria to each assembly. This program has presented the essential information required to successfully use lead-free solder alloys in hand soldering operations. We discussed the reason for the switch to lead-free and the characteristics of the alloys. Then we presented the details of the soldering operation. And we concluded with how to evaluate a lead-free solder joint. The more time you spend hand soldering with the lead-free alloys, the more confident you'll become about creating and evaluating reliable lead-free solder joints. And you'll be helping the environment too.